Hello and welcome to this presentation on differentiation applications. We're going to specifically look at rates of change. This presentation does assume you understand basic differentiation, the product rule, and also successive differentiation. Some reference information here. Obviously standard derivative tables we'll be using. We have our standard function of y and our derivative dy by dx here. The use of the product formula for non-standard differentials, dy by dx is equal to u times dv dx plus v times du dx, the product formula there, and also awareness of successive differentiation. Given a function of y, we can find the first differential, dy by dx, or function dash x, and the second differential, d2y by dx squared, or function double dash x. Considering here application of rates of change, if quantity y depends on quantity x, we often write the rate of change of y with respect to x as dy by dx. We're talking about pressure. The rate of change of pressure, P, with height h, can be written as dp by dh. Usually the rate of change is respect to time unless otherwise stated. We can also have, in terms of electrical work, we could have rate of change of current with respect to time, so di by dt. We could have rate of change of temperature with respect to time, d theta by dt. So various examples of notation we might be using. Sample 1. The length L in centimetres of a small metal specimen with temperature 0 degrees C is given by the expression L equals to 1 plus 3 times 10 to the minus 6t plus 50 times 10 to the minus 9t squared. We're asked to find the rate of change of length with respect to the temperature, capital T, when the rod's temperature is at A, 300 degrees C, and B, minus 75 degrees C. So the first thing we need to do is, given the equation for L, we need to differentiate it to find the dL by dt. So differentiating a constant, it disappears. Differentiating 3 times 10 to the minus 6t, and notice that it's in the form of ax to the n, that differentiates to 3 times 10 to the minus 6, and differentiating 50 times 10 to the minus 9 t squared differentiates to 2 times 50 times 10 to the minus 9 t. Tidying that up, we get dl by dt is equal to 3 times 10 to the minus 6 plus 100 times 10 to the minus 9 t. Now continue example 1 here. Part A says to use this equation, dl by dt, to find the rate of change when the temperature is equal to 300 degrees C. All we do is take our dl by dt equation and simply put the value of t is equal to 300 where we see a t in the expression. If we evaluate that expression, we get 33 times 10 to the minus 6 centimetres per degree C. Part B, similar kind of thing, it's just that the temperature now is minus 75 degrees C, but again all we do is put the value of minus 75 in the dl by dt equation, and that gives us the value of 25.5 times 10 to the minus 6 centimetres per degree C. Just be careful of your negative numbers in part B. Question 1a. The luminous intensity I, candelas, of a lamp of varying voltage V is given by the expression I equals to 0.8 times 10 to the minus 3 V squared. We've got to calculate the voltage at which the light is increasing at a rate of 2.4 candelas per volt. That's a rate of change. So the first thing to do is to take the equation I given and differentiate it. So I is equal to 0.8 times 10 to the minus 3 V squared. This is a standard form, ax to the n, so we know our solution. So di by dv is 2 times 0.8 times 10 to the minus 3 V. Tidying that up, di by dv is equal to 1.6 times 10 to the minus 3 V. We're given a condition that di by dv is 2.4 candelas per volt. Now be careful here, we are actually given the rate of change. So we are given the left hand side of the equation here. We've got to solve for the right hand side. So 2.4 is equal to 1.6 times 10 to the minus 3. Simply rearranging this now, V is equal to 2.4 divided by 1.6 times 10 to the minus 3. hence V is equal to 1500 volts or 1.5 kilovolts. Question 2a relates to Newton's laws of cooling. We're given an expression for temperature that theta is equal to theta naught e to the minus kt. If you read the question, the theta naught is a constant of 8 degrees C and the k is a constant of minus 0.02. We're asked to find the rate of change of temperature with respect to time after 20 seconds. So the first thing we need to do, given the equation in the question, is to differentiate it to find the d theta by dt. The e to the minus kt is a standard form in our table. It's e to the ax in our table, and we've got the solution for that there. So the d theta by dt will be minus k times theta naught times e to the minus kt. I'll let you think that through. We're then given that t is equal to 20 seconds, theta naught is 8, and k is equal to minus 0.02. And now simply put those values into our expression. So put the k value in, look out for the double negatives there, put the theta naught value in, and again the k and the t go in the exponential. Evaluating our function, evaluating the exponential, and simplifying, we end up with d theta by dt is equal to 0.239 degrees C per second. Okay, here we're going to consider the relationship between distance or displacement and velocity and acceleration. We're going to use successive differentiation here. If distance is given in terms of x and t in terms of time, then if we have an expression for x in terms of a function of t, say for example x equals to 2t cubed minus 4t squared plus 5t. If we differentiate that equation with respect to time, we get dx by dt, which is actually velocity. So if you find the gradient of a point on a distance time diagram, you actually get its velocity. So taking the above example, we would get v equals to 6t squared minus 8t plus 5, and that's all standard form differentials. If we was to differentiate the velocity equation again, successive differentiation here, we would get the acceleration time expression, the dv by dt, and in this case, using our example, a would equal to 12t minus 8. In other words, finding the gradient on the velocity time diagram gives us the acceleration. Summarising the previous slide, if a body moves a distance x meters in time t seconds, we have an expression for x is some function of t, and that relates to the distance. If we differentiate the distance with respect to time, we get velocity, v equals to dx by dt, that's the first differential, or sometimes written as f dash t in this case. And if we continue differentiating, we differentiate our velocity again, we get acceleration a, which is dv by dt, or sometimes written as f double dash t, or d2x by dt squared. They all mean the same thing, but basically that is the acceleration in terms of function t. Okay, question 3a here. The displacement s in centimeters of the end of a spring at time t seconds is given by the expression s equals to a e to the minus kt times by sine of 4 pi ft. We've got to calculate the velocity at the end of the spring after 1 second. We're given a is equal to 2, k is equal to 0.9, and f is equal to 2.5. Now the first thing we need to recognise here is they've asked for velocity, but they've given us a distance time function. So we're going to have to differentiate the s function given to find the velocity function. So the first thing is noting s is equal to a e to the minus kt sine of 4 pi ft, that this is actually a product. So we're differentiating a product here. We've got a function of t, the e to the minus kt is a function of t, and also the sine of 4 pi ft is a function of t, and they're multiplied together, so they're a product, so we must be aware of that. First of all, let's take the information from the question. We know a is equal to 2, k is equal to 0.9, f is equal to 2.5. We've simply first of all put them into the s equation. So in goes the a, in goes the k term we've got there, and in goes the f term there. So simply putting in the terms given in the question into the equation. That simplifies to give me s equals to 2e to the minus 0.9t multiplied by sine of 10 pi t. Now question 3a here continued. I've repeated the formula for s for convenience. Now this is a product, so we need to use the product rule. The first thing we need to do with the product rule is define our u term and our v term. I'm going to make my u term equals to 2e to the minus 0.9t, and my v term is equal to of sine 10 pi t. So knowing that, we can now differentiate using our standard derivatives. So if u is equal to 2e to the minus 0.9t, then we can find du by dt by differentiating. I'm using the standard form here of e to the ax goes to ae to the ax. We end up with a du by dt equals to minus 1.8 e to the minus 0.9t. I'll let you check that for yourselves. We've let v equals to the sine of 10 pi t, so again differentiating that with respect to t, we get dv dt, and using our standard tables we get 10 pi times the cos of 10 pi t, and I've used this function in the table. I'll let you again think of that. So now looking at our product formula, all I'm going to do now is put the above four terms into the product rule. So the u from above is the 2e to the minus 0.9t, and that's multiplied by the dv dt from above is my 10 pi cos 10 pi t, and I'm adding to that my sine of 10 pi t, which is my v from above, and I'm multiplying that by minus 1.8 e to the minus 0.9t, which is my du by dt term. If I simplify that, just factoring on the e to the minus 0.9t and multiplying the 10 by the 2 in this term and simply rearranging this term, I end up with an expression for ds by dt. Okay, question 3a continued. I just repeated my ds by dt equation for convenience here. Now it's all about using the equation. We've got to find the velocity, ds by dt in this question, when time t is equal to 1 second. All we do now is put the value of 1 where we see a t in the ds by dt equation. So we see t's here, we put a 1 for the t. That's all we're doing here. Okay, the rest of it from here on in is arithmetic. If you do the numbers on this, you get cos of 10 pi, and don't forget we're using radians here. Your calculator must be in radians mode, but cos of 10 pi you will find will give you 1 in radians mode, and then sine of 10 pi you will find gives you 0 in radians mode. Okay, the rest of it's all arithmetic, and we eventually find our velocity, or our ds by dt, as 25.546 centimeters per second, or I've also stated it in millimeters per second here. Okay, example 2 here relates to our previous slide on the relationships between distance and velocity in time. We're given here an expression for distance of a car's motion, and it's x equals to 6t cubed minus 5t squared plus 8t minus 2. We're asked to calculate the velocity and the acceleration given some time periods, t is equal to 0 and t is equal to 1.2 seconds. So implicitly we have to understand that given the distance time equation, we have to differentiate it twice. We differentiate it once to get the velocity expression, differentiate it again to get the acceleration. So it's a standard polynomial differentiation here. Given the x equals to 6t cubed minus 5t squared plus 8t minus 2, if we differentiate it to find the velocity equation, so v is dx by dt is the standard forms here, we get 18t squared minus 10t plus 8. I'll let you deal with the standard differentiation there. And if we differentiate again, we find the acceleration equation, the a, which is dv by dt, or the second differential of x. It could be d2x by dt squared, and that's equal to 36t minus 10, and that's meters per second squared unit. And again, I'll let you look at the differentiation there. It's all standard formed, all ax to the n polynomials. Okay, continue with example 2 here. I just repeated the velocity and acceleration equations from the previous slide. all we're going to do now is to use the equations for the time intervals given. Part A says calculate the velocity when time t is equal to 0. So all we do now is put the value of 0 into the velocity equation. Okay, wherever we get a t, basically we're going to put the value of 0 and work out the velocity. It's 8 meters per second. We're going to do the same for the acceleration. Time t is equal to 0 again. We just simply put a 0 wherever we see a t in the acceleration equation. That gives us minus 10 meters per second squared, which is actually a deceleration in this case. For part B, we're now told the time is at 1.2 seconds. So again, same process. For the velocity equation, we simply put the 1.2 wherever we had a t and work out the value. That gives us 21.9 meters per second. And then finally, for the acceleration equation, put the value of 1.2 in the equation, and that gives us 11.6 meters per second squared acceleration. So question 1b, we're told that a large package is dropped from a helicopter. It falls a distance x in time t interval, and the expression given to us is x equals to g times t squared divided by 2. We're asked to find the velocity and the acceleration of the package after it's fallen for 2 seconds. We've got to state any assumptions we're making. So given the expression for distance, the x is equal to half gt squared. The assumption we'll make here, of course, is that g is equal to 9.81 meters per second squared. So we're going to assume that value. We're allowed to assume the value of g. And then, as it's asking us for the velocity and the acceleration, we need to realise that we differentiate the x with respect to t to get the dx by dt, or the v expression, and that will be standard form give us g times t. Again, I'm using the standard form ax to the n. I will let you review that. And then to find the acceleration, we just have to differentiate the expression one more time. So the dv by dt, in this case, the velocity with respect to time, actually will give me the value of g, the 9.81. And again, I'll let you follow that through from the standard tables. We then simply use the equation when t is equal to 2. So for velocity, the equation will be 9.81 times the t, times by the 2 in this case. The velocity after 2 seconds is 19.62 meters per second, and then the acceleration equation A is going to be 9.81 meters per second squared, which we would know. Question 2b relates again to distance in x in meters of a vehicle travelling after time t seconds. The brakes are applied. So this is the distance travelled once the brakes are applied. So x is equal to 20 times the t. Take away, that's basically there 5 times t squared upon 3. We've got to determine the speed of the vehicle in kilometres an hour, so we'll do a conversion later on. At the instant the brakes are applied, and then find the distance the car travels before it comes to a stop. So given the distance expression, that x is equal to 20t minus the 5 upon 3 times t squared. We differentiate that, again we've got standard forms here, to find the velocity equation. So v, the dx by dt, is equal to 20 minus 5 upon 3 times by 2 times by the t. That simplifies to 20 minus 10t upon 3. I'll let you look at the calculations there. And then the acceleration, the a, is now dv by dt, and again differentiating the velocity, we get minus 10 upon 3. The constant 20 disappears and the t disappears from the standard tables. So now we can use the equations we've derived. We've got to find the speed of the vehicle at the instant the brakes were applied. So we need to understand here that that will be at time t is equal to 0. Okay, so using the velocity equation to find the speed, v is equal to 20 take away the 10 times the 0, which is the t, and that's all divided by 3. So we find 20 meters per second is the speed that the vehicle was doing at the instant the brakes were applied. They've asked us to convert that into kilometers an hour, and here's the unity bracket conversion if you want to follow that through to get the 72 kilometers an hour. And then part B, we're asked to find the distance the car travels before it comes to a stop. Now again, we need to think this through, but when it comes to a stop, then the velocity will actually be 0. So v is equal to 0 in this case. So we're going to take the velocity equation and we're going to make the left hand side of it equals to 0 because that's its speed when it comes to rest. The right hand side we will get 20, take away 10 times t divided by 3. So the only unknown we've got in this equation is t, and we can then rearrange the equation, a little bit of transposition there, basically add the 10t upon 3 to both sides and then multiply by the 3 and divide by the 10. You'll get the expression for t, and if you put the numbers in, that will give you 6 seconds. So the distance travelled, going back to the distance equation, now we know the time taken for the vehicle to come to rest. We can go back to the first equation, which relates to distance, and put the 6 seconds into that equation, and we can find the distance that was travelled before the vehicle came to rest, and that's 60 metres. Question 3b relates to angular displacement, theta, this time in radians, of a flywheel in time t. They've given us the expression of theta is equal to 9t squared minus 2t cubed, and asked us to find in part A the angular velocity and the angular acceleration when the flywheel is at time t 1 second. So that will implicitly mean we have to differentiate once to find the angular velocity, differentiate twice to find the angular acceleration, and then in part B we've got to find the time when the angular acceleration is 0. So taking the original equation for displacement theta, 9t squared minus 2t cubed, that's all standard form of ax to the n. If I differentiate that to find my angular velocity, so my first differential here, d theta by dt, I'll let you review the standard form there. That gives me 18t minus 6t squared in radians per second for the angular velocity, and then if I differentiate again to get my second derivative here, to get my alpha term for angular acceleration, so the d2 theta by dt squared here, again looking at the standard differential, that gives me an angular acceleration equation of 18 minus 12t in radians per second squared. So question 3b continued, part A here, to find the angular velocity and acceleration of the flywheel at time t is equal to 1 second, I simply put the value of 1 into the angular velocity equation, so the 18t minus the 6t squared, I simply put in 1 for the t's there, that gives me 12 radians per second, and to find the angular acceleration alpha, again using the angular acceleration equation, I simply put the value of t is equal to 1 into the equation, and I find that the angular acceleration is 6 radians per second squared. To find the time when the angular acceleration is 0, so alpha is equal to 0, this time I take my angular acceleration equation, but on the left hand side I make it 0, and on the right hand side I've got my 18 minus 12t, and then to find the time I simply rearrange for t, so add 12t to both sides and then divide by the 12. So 1.5 seconds is the answer. And final question here, question 4b, relates to displacement x of a valve in a car engine. Is given by the expression x equals to 2.2 times cos of 5 pi t plus 3.6 times the sine of 5 pi t. We've got to find the velocity after time t is equal to 20 milliseconds. And be careful of that, it's 20 milliseconds, so we'll have to convert it to seconds when we come to use it. Now, this is a standard form question. Some of you might be thinking, oh, it's a product here. No, it's not a product, because we've just got in each term one function of t. We've got 2.2 cos times a 5 pi t. That's a one function of t, and added to, not multiplied to, added to the next function of the sine function. Again, that's just a single function of t. So this is not a product. It's a standard form solutions of sine ax and cos ax. So the displacement x in this case, 2.2 times cos of 5 pi t plus the 3.6 times the sine of 5 pi t. To find the velocity equation, we've got to differentiate the x with respect to t, and again this is standard form differential. I will let you work this through on your own, but you'll end up with the velocity equation, or dx by dt, as being 18 pi times cos of 5 pi t, take away 11 pi times the sine of 5 pi t. Okay, question 4b continued here. I need to find the velocity when time t is equal to 20 milliseconds. Notice I've put my milliseconds into seconds there, so 0.02 seconds I will be using, and I simply put that value into the velocity equation. Wherever I see a t in the equation, I put 0.02. I'll let you do the number crunching on that. You should find the answer for velocity is 0.431 meters per second. I'll leave you with some further questions to look at here. The answers are in the brackets on the right hand side, and I would encourage you to look at the reference source I've used here for the slides for further information. Thank you for viewing.